record in fourth block yesterday. There's just so many people in that room. I get nervous and I forget what I'm doing. Yeah, we dropped down to like 27. Now we're back up to 29, and I keep getting new people coming in from different schools. Like it's just what it is, but it'll level out eventually. Okie dokie, rock and roll. So doing a little. Let me get all my favorite colors up here, so I'll be good to go. I like a little pink, a little purple, and let's do a little royal blue because I like it better. All right, rock and roll. So domain and range, okay? Basically, what does domain refer to? The x values, yeah. So domain, we're referencing our x values that work. And range, we're referencing our y values. Okay. You'll see a combination of interval notation for domain and range. That's where we use the parentheses and the brackets. They'll also use inequality notation, so they just expect you to be able to read both, okay? And then whatever notation you prefer, they will accept in terms of your answer. So they will take either notation. You'll catch me primarily doing interval notation just because it's a habit. It's just a habit. So let's jump in and let's actually look at a couple of functions that hopefully aren't too foreign to us. The first one, y equals x squared, what does that look like if we were to graph it? That's our parabola, right? And so if we think about the domain, what x values work? All of them, yep. So options, right? You can do the real symbol, which is the R with the leg, or you can do ARN, all real numbers. They accept that. They understand that abbreviation, right? Or we could do negative infinity to positive infinity. Okay, so any of those three notations are acceptable when they're grading your work in AP. What about range for that one? It's all the positives, okay? And in fact, it does equal 0. So you could say, there's a couple of ways to say that. This is what I would say. I would say 0 to positive infinity. All right, using that bracket on 0 because 0 squared is 0. Some people would say this, all real numbers, x greater than or equal to 0. All right, so that's an option as well. Okay, so 2 options there. So take a second and play with the rest of those. See if you can find the domain and range. Double check that with the table, and then we'll go over and make sure we're correct, and then move on from there. Anybody else in here taking bio? Yeah. How's that going so far? Or is it going good so far?
Oh, we haven't.
Oh, y'all haven't met yet?
Yeah.
Oh. When do y'all start?
Tomorrow.
All right, tomorrow.
Oh my gosh. Never showed up. So proud of you.
Bless. All right, so let's look at the first one. So square root of 4 minus x. Is there going to be something about this one that's going to be an issue? Okay, especially if we're thinking about a graph. With square root of 4 minus x, what can't happen? Yeah, perfect Nugan. I was like, y'all just looking at me, and I'm like, what? Here we go. Okay, yay. All right, so with the square root of 4 minus x, what is going to be an issue with that one? Yeah, we got to have a positive number under the square root, okay? Can we have a 0 under the square root? Can we take the square root of 0? Yeah, okay. If that expression were in a denominator, could we take the square root of 0? No. All right, so knowing the difference between where it's located would be important. All right, so basically what's under there, 4 minus x, has got to be positive, which if we just work through that, x is going to have to be less than 4 if we want it not to be a negative. It's okay if it's equal because 0 is going to be all right. So for our domain, negative infinity up to 4. Right. So now if we think about our range, all right, if we put 4 in there, obviously that's going to give me a 0, so 0 is going to work. If we put 3 in there, we're going to get a positive number. If I put 2 in there, a positive number. So our range is going to be 0 to positive infinity. Okay, that function itself will always be positive. It's a nice little square root function. Okay. What does that third one look like when we graph it? 1 over x. I remember. Well, if I put a 2 in there, 1 over 2 would be 1/2. 1 over 1 would be 1. What would 1 over 1/2 be if I put 1/2 in? Yeah, be 2. This is your reciprocal function. All right, so whatever you put in, it's the reciprocal of it, which means if I graph it, it's staying in those diagonal quadrants, okay? So just a rational function. We have to take my This is not Will, so we had to take him. Oh, he hates going to the vet, and he had to go back for some blood work today. But he's so, Beagles are super aware. My husband said when they got to Domino's, he started crying because he knew where he was going. God love him. Okay. So for our domain on this one, what's definitely not going to work in this reciprocal function? For x, 0. Yeah, that's going to be a big no-no. So you could do it one of two ways. I would say real numbers, x not equal to 0. All right. Or you could do negative infinity to 0, then 0 to positive infinity if you wanted to do 2 intervals. All right. What about your y values? What's not going to work? A 0 again, right? We're not going to get 0. The only way to get 0 is if the numerator is 0. So it's going to be the same. All real numbers, x not equal to 0. Okay. All right. Little geometry trick question for you for the next one. Anybody know what that one looks like when you graph it? You got a square under that square root. Well, what if I did this? I'm going to undo this equation a little bit. I'm going to square both sides. So I'd get y squared equals 1 minus x squared. It's a semicircle. All right, so that equation I can tell if I move the x squared over, it would be a circle. But I don't have that equation. I have a square root, which means I have a semicircle. I have half of it. Okay, so this is a semicircle. Right? What's the radius of that semicircle going to be? What number's under that radical? 1. If I take the square root of 1, what is it? It's 1. That's going to be my radius. Why do I know that it's the top half of the semicircle? It's not negative. The radical's not negative. Okay? I have a positive radical, so it has to be the top half. What kind of sandwich are we eating? I know I just love foods. That's what I'm asking.
Turkey,
Mmm.
mayo, lettuce.
All right. You ever put honey and apple on a green apple on a turkey sandwich? Change your life. Little bacon.
Bacon, yes.
Okay. Little bacon. Little thinly sliced Granny Smith apple and a little drizzle of honey. Yep. Change your life. Okay. All right. So now that we know it's a semicircle, sorry. Y'all know I'm easily distracted. Okay. Especially by food. Okay. Nobody was at my house last night, so I ate cereal for supper. It was fantastic. I have this protein cereal. It's so good. All right. So my domain, what are my x values going between? -1 and 1. Okay. What are my y values going between? 0 and 1. Okay. So semicircles have a finite domain and range. All right. Now, why is this important? Well, as we transition into calculus, there will be times where we have to know how a function behaves, so that we know whether or not it's going to be included in our answer or not. Where are the issues with it? If I have, like in this rational function, 0 is a problem. All right, it's not defined for the domain or the range, and things like that. So you will do a lot of not necessarily writing the domain and range, but thinking about the domain and range because it'll affect your answer. Okay. All right, so let's jump over here. Again, just doing a little practice. I think I went too far. Did I? No. Okay, let's see what we got next. All right, we got the toolkit of parent functions. I've got mine out of order. It's like, what's wrong with mine? Aha. Okay, so these are all the parent functions that we need to know. You've got to be able to just kind of work with those. At any point in time, we know that x squared is our parabola, x cubed, square root. It has a finite starting point. What's cube root look like? Walk like an Egyptian. All right, it takes that cubic and turns it sideways. All right. 1 over x we just did. That's your reciprocal function. And then this last one, this is your semicircle. That looks like I misspelled circle. But the square root of a squared is your radius. Just as a heads up. So those are just ones that we'll see often. Okay, and being able to manipulate those as needed. All right, but I want to show you some new ones. All right, some new parent functions that we'll see throughout calculus. The good news is most of the times when we're dealing with these, we can plot a few points and figure out what they're doing. Okay, so the other ones are pretty common knowledge. We've worked with those for several years. But now when we get to calculus, we want to look at some new ones. So here's one. Let's just see if we can kind of think our way through what it might look like. 1 over x squared. Okay, looks similar to that 1 over x reciprocal function. What's different though? We're squaring it. And what happens when we square something? It's going to always be positive. So because it's a reciprocal, the positive part stays positive. Guess what we do with the negative part? It becomes positive. We flip it up. Okay? If I take a negative x value and I square it, it would be positive. So instead of diagonal quadrants, they are in consecutive quadrants. Okay? Or adjacent quadrants. So 1 over x squared, we flip it up. Okay, that negative side. All right, so this one, y equals x to the 3 halves. So fraction exponents, okay? Remember, that's the same thing as the square root of x, and we're going to cube it, okay? So that means the same thing, the square root of x, and we're going to cube it, okay? So let's just think of that a little for a second. If I put a negative x value in there, can I take the square root of that negative? No. So I'm not going to have anything on the negative half of the x axis. So it's going to all be on the right. If I put 0 in, 0 cubed is still 0. Right? If I put 1 in, the square root of 1 is 1. I cube it, and I get 1. Okay? I'm probably not going to do 2, but I might jump out here to 4. Okay? What's the square root of 4? It's 2, and 2 cubed is 8. So this is like a square root graph, except it's growing really quickly. Okay, so it looks a lot like a square root graph. It's just going to grow a lot quicker. Okay. Hold on, they've sent us a big list of people they want us to send to the library. Janelle Moore, Stephen Neal, Madison Norris. Okay, none of y'all. Yay. Has everybody got their iPad in here? Okay, then I'm going to ignore all these text messages that are about to come through. Okay. All right. Then this last one's one of my favorites. Okay. Similar to what we just did. Okay. Except they flip that fraction on us. And so we have to the 2/3. All right. So that would be the cube root of x. And then we're going to square it. Okay. So we can take the cube root of negative numbers. Right. But what's going to happen when I square them? They're going to become positive. So everything's going to stay above the x-axis, all right? If I put 0 in there, 0 cube root of 0, 0, 0 squared is 0. So I'm going to have a 0, all right? But let's put 1 in. Cube root of 1 is 1. 1 squared is 1, all right? If I put a negative in, cube root of negative 1 is negative 1. Square it, I get positive 1. So the good news is whatever happens on the right is also going to happen on the left, right? So let's see. I don't want to put 2 in there, but I'd put 8. All right. 1, 2, 3, 4, 5, 6, 7, 8. All right. So the cube root of 8 would be 2, and 2 squared would be 4. So we get what I like to refer to as this bird graph because it's going to happen on both sides. All right. Again, you can always just check some points. It's not necessary that we memorize it, but these are ones that we're going to use on the regular. All right, and see and do a lot of analysis with. All right, transformations of functions. Again, understanding what's happening within the equation, what it does to the graph, how it changes it. All very important for what's ahead, okay? There are lots of different transformations. Right. So let's just put some letters in there. Okay, so lots of things going on. All right, so the first thing we need to know is that coefficient out in front is our vertical stretch or shrink. If it's negative, what does it do to the graph? It flips it, okay? So that's our vertical stretch and shrink, right? B is our horizontal stretch or shrink, and we always divide. Okay, so it's always a reciprocal. Right? It divides our x value. Okay. And then for C, we do the opposite, and that's going to give me my horizontal translation. How far do I go left and right? And then D, we keep the same, is our vertical translation, up or down. All right, so let's look at this one. It's got a little bit of everything in it. The only thing that's weird for me is inside of this parenthesis, there's a 2x there, and typically we don't see that. So how could we fix that so that it looks like that general equation I wrote up there? We don't really want to divide. We want to factor because we want to keep everything. So inside that parenthesis, I'm going to factor, which will leave me 2 times x minus 2, and then my squared plus 3. Okay, so that we can see all of the manipulation for the transformation. Okay, so be sure to factor. What is my parent function for this one? What shape's it going to be? It's parabola, y equals x squared. Okay, and I like to think about my parabola in terms of its basic points. -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. You don't necessarily have to do that, but it just helps me when I do those stretches and shrinks. Okay. Where are we going to move this parabola on the coordinate plane? What are your translations? All right, we're definitely going to go up 3. Does it have a horizontal translation? Yep, it's inside that parenthesis with the x. So if it's -2, which way are we going to send it? Right 2. Okay, so we're going to go right 2 and up 1, 2, 3. Right, and when I get ready to graph, I'm going to graph from that little spot right there. Let me zoom into that a little bit so I can see it better. Okay. Now, we have a vertical stretch or shrink of a -2. Basically, that means I'm going to change my y values. I'm going to multiply them by -2. And so if we do that, my y values are going to be -8, -2. That should be a 0. 0, -2, -8. Okay, so those are going to be my y values we want to graph from our new spot. And then the 2 inside says we're going to divide x. All right, so we're going to divide x by 2. And so if we do that, -2 divided by 2 is -1. -1 divided by 2 is -1/2. 0 is still 0. A 1/2 and a 1. Okay, so I'm just going to kind of rewrite the table. And so then we're going to graph from our little X marks the spot. So left 1 and down 8. 1, 2, 3, 4, 5, 6, 7, 8. Left 1/2 and down 2. 0, 0 gets to stay. And then we're just going to repeat it on the other side. And so he became a really skinny parabola who's turned upside down. Right? So understanding how all the transformations work. If you remember, we did all of that with the trig functions too. We'll talk about that tomorrow. using our trig functions. Okay. Question about that. It's just been a hot minute since we've done it. Okay, just wanted to refresh your memory. All right, all the things that are important, big algebra topics. Okay. All right, rock and roll. Let's jump over here. Even and odd. Okay. All right, remember with an even function, f of negative x is the same thing as f of x. That's how we have to prove it. Okay, in other words, if I have the ordered pair AB, I also have the ordered pair negative AB. Okay, so if the x's change, the y's stay the same. Okay. An even function, if we're looking at it on a graph, is symmetric about the y-axis. Okay, and then if we have an odd function, f of negative x is the same as the opposite of f of x. In other words, if I have the ordered pair AB, I'd have the ordered pair negative A, negative B. And odd functions are symmetric about the origin. Again, just understanding the characteristic is good. It's not that we'll do a ton of work proving that something's even or odd. It's just us knowing for sure which one it is. It will help us in some of the other things we're going to do. Okay, so all the algebra. How do we do it algebraically? How do we go in and prove whether or not something's even or odd? Remember? Yeah.
I'm not sure. I'm just gonna try to look. If all what you call the numbers in front of the
All the coefficients.
yeah, coefficients, and they're all adding their equal, and they're yeah, all the coefficients and the exponents add up to an even number, then it's even.
That's a good try, right? We know that if we look at the, I think what you're thinking about is in terms of when we're graphing, we're trying to figure out the end behavior. Yeah, so that's what you were thinking about, where we look at the major exponents. If it's an even one, then it's going to look like a U. If it's odd, it's going to look like a snake. That comes in our graphing. Good. All right. All we're going to do is plug in a negative x. Okay. If all the signs change, then it's odd. If everything stays the same, then it's even. Okay. So with this one, if I plug in a negative x, so I have negative x plus 1. Did every sign change in the original? No. Okay. Did every sign stay the same to the original? No. So this one's neither. Okay. If I go to the second one, again, I'm going to plug in a negative x. So I want negative x. I want to square it and add 1. We're going to simplify. If I square a negative x, what do I get? X squared plus 1. Did every sign change or did every sign stay the same? Same. So this one's even. Okay? And so that's how we do it algebraically to justify. We look back at the original. Did all the signs change or did they all stay the same? Okay. And then we get to piecewise functions. And people love to hate piecewise functions, but I just want you to know everything we learn how to do, we'll do it with a basic function, and then we'll do it with a piecewise, okay? Because life in general is a piecewise function. All the pieces come together. We're hardly ever just one solid track, all right? So with a piecewise function, I just caution you to look at each piece individually, all right? So consider each piece individually and heed, that's a good word, the domain restriction. Helps if you can write. Right? So let's take a look at this piecewise function. Let's graph it. Okay, it gave me a graph grid here, so let's graph it. I'm going to start with the top piece, all right? And just looking at the top piece, we've got f of x equals negative x, or y equals negative x. If I was just going to graph that and it was not a piecewise, what would it look like? It'd be a line. What kind of slope would it have? Negative slope, okay? So it says everything that's less than 0. So I'm actually going to start at 0. And if I do the opposite of 0, it's still 0. Now, notice there's no bar underneath that 0. So at 0, 0, I'm going to put an open circle. It may get filled in later by another piece, and that's okay, all right? And then we just want to do that line with negative slope to the left. So it has a slope of 1 over 1 to the left that's negative. And so I'm just going to sketch that piece in. Okay. All right, then we go to our second piece. Our second piece is y equals x squared. What does that typically look like? That's our parabola, okay? We're going to start at 0. Well, 0 squared is 0. I can include it, so I'm going to color in that point. All right? At 1, 1 squared is 1. It, too, has a bar under it, so I'm going to color it in and put a little bitty curve right there. All right? It'll be hard to see, but it's okay. And then the last one is the equation y equals 1 anytime x is greater than 1. What does y equal 1 look like? Horizontal line. So because we've already included with the blue, we can just pick up right there and extend out for the 1 forever. And there's our graph. Okay. Now, I didn't ask you this, but what's the domain of that function? All real numbers, okay? We've got arrows on both sides. Any x value we put in is going to work, okay? What about my range? 0 all the way to positive infinity. Yep, and that would be our range, okay? So we'll do several things where we'll graph and then all that good stuff, all right? The main reason that we have to think about, piecewise functions is because absolute value by definition is piecewise. And once we start doing limits and we start doing derivatives and integrals, anytime we mess with absolute value, we have to rewrite it as a piecewise function. Okay, so it's just one of those things that we'll constantly do. So when we think about y equal to the absolute value of x, all right, by definition, all right, if I put a positive number inside of absolute value, what will it always spit out? What's the absolute value of 5 would be 5. It would be positive. So whatever I put in, if it's positive, will stay itself. It does not change. Okay? But if I put in a negative number, okay, what happens to that negative number? It becomes a positive. It becomes the opposite of what I put in. So that piece is the opposite of x, because if I put a negative in, I get a positive out. So the opposite of a negative is a positive. All right, and that's where that definition comes from, and we will use it a lot. Okay, so just as a heads up. All right, don't forget composition is a two-part process. All right, f of g. All right, they like that notation. They also like the double parenthesis notation for composition. All right, start on the inside. and work your way out. Okay. All right, let's do a little composition. We've got done. Okay, for all things functions. All right, here we go. So let's look at this one. It says f of x is equal to x minus 7, g of x is equal to x squared. See if you can do the numerical one and then try the algebraic one for me real fast. All right, let's check that first one. So we'd start with g at 2. All right, so g at 2 would be 2 squared, which would be 4. So I need f at 4. And so 4 minus 7 would give me negative 3. Okay. And then when we do the second one, g of x plus 2 basically says I'm going to take x plus 2 and square that. And then I'm going to plug that in everywhere I have an x in f. So that would give me x plus 2 quantity squared, and then minus 7. Let's simplify that because we can. So that would give me x squared plus 4x plus 4 minus 7, or x squared plus 4x minus 3. All right, so just a little algebraic manipulation there. Okay, so we want to simplify those as best we can. And then the final thing that we will actually do is decomposition of functions. We will break a composition apart. All right, remember when we decompose something, we're looking for f of x and g of x being the inside function. That's something that's going to be inside parentheses in a denominator under a radical. And then we have h of x. What are we doing to that outside function? To that inside function. So we're squaring it, we're taking a square root, we put it in a denominator. something like that. Okay, what did we do to the inside? Okay. And this is important when we start talking about integration. So our inside function and our outside function. All right. Remember, there's multiple things, all right, or multiple ways we can do a decomposition. We will find there's always a best decomposition when we're doing integration. All right. But let's take a look at this one. All right. So we're looking for f of x and g of x. G of x being our inside, f of x being our outside. What do we have here that is in a parenthesis or something crazy? In our h function. Yeah, the x minus 5. That's probably what I would choose. Okay. And then what are we doing to that x minus 5? Well, there's a 3 on top, and then we're raising it to the 5th power, so we just put an x there. All right, meaning that's what I'm raising to the 5th power. We could also have said that the whole denominator was the inside. And if that was true, what would the outside be? Yeah, just 3 over x. Okay? So either one of those is an accurate decomposition. Okay? But again, we'll focus on the best decomposition at some point. All right? So that's it in terms of review. Now, one of the things that I did not review with you guys were log properties, okay, solving log equations, exponential equations. We're going to do a problem tomorrow where we solve an exponential equation, just, in a warm-up, get used to that again. But I want to give you a couple of hints, because at this point you should be able to do everything on your TWIS except for the trig ones, and I think there's 3 of those. So let me give you a couple of hints. So did somebody not get one? Because there's another paper, there's an extra paper copy on the back table. Okay, yeah, because I didn't put it electronic, so be sure you grab that. All right, here's the hint for number 3. All right, the compound interest formula. It helps if you can spell. God bless it. Okay. So that's A equals P times 1 plus R over N to the NT power. All right, R being our rate, N is our number of compoundings. Right? So that's exponential. I don't think you need this one, but I'm going to give it to you anyway. Compounded continuously. So we only use that when they say that word, continuously. That's PE to the RT, E being that Euler's function. And then number 5 asks you to verify an inverse. To verify an inverse, it takes 2 compositions, right? So f of f inverse, and it should leave you with just an x when you finish. And then if you switch the order, f inverse of f. Okay, so both of those have to work in order to verify. Okay, both must work. I think those were the only 2. Yep. Okay. You can look up your log properties. I think it'll help you with number 6, okay, and solving that equation. On Friday, like I said, we'll come in and we'll kind of talk through this, all right, make sure we got it together, that we're good, all right? But over the next couple of days, work on this TWIS. There's just 2 questions. So, and in fact, you've got about 20 minutes today you can work, all right, if you want to work on that while you're in here, all right, the ones that we've talked about. And then using those hints, okay? Then tomorrow we're going to do all things trig. It'll be a lot, okay? We're going to come in hot and heavy with the trig tomorrow, okay? All right, all right. Good job.